I promise that I'm gonna give you normalizing flows, but recurrent neural networks, you can also replace them with ODs. For normalizing flows, what are they? Somebody gives you a distribution. Maybe this is your density, or this second option could be the density of your data. And this is just two-dimensional. This is x coordinate, y coordinate, and the color is visualizing the density. So you can either plot it in 3D or you can plot it in 2D. And that's what we are plotting. That's your density. Or this other figure could be your density, your probability density, or the third one could be your probability density of the data. And here you have only two features. For an image, it's going to be extremely high dimensional. And what do you want to do? You want to approximate this distribution. So now we are starting to go beyond classification. Okay? Somebody gives us a density, we want to approximate. It is similar to what GANs does, but GANs is trying to generate samples from your density. Now you want to actually know what your density is. There is this change of variable theorem. So I'm just gonna introduce normalizing flows, and then we are gonna extend this to continuous time normalizing flows using ODEs, okay? So this is pretty standard. The change of variable theorem in probability is gonna be like this. Somebody gives you Z0, maybe you're sampling from a normal distribution. We can push it through a neural network or a complex function, and that's gonna give you complex samples from a more complex distribution than normal or uniform distribution. You're gonna assume F is bijective for normalizing flows. It means that it has an inverse. There is a one-to-one correspondence between your inputs and outputs and vice versa. If that is true, then you can write down the probability distribution of the random variable Z1 in terms of the probability distribution of random variable Z0. How? Forget about these logs. It's going to be P of Z1 is equal to P of Z0 times, this is where your function is going to come in, the transformation, times the absolute value of the determinant of the inverse of the gradient of your function with respect to Z0. So that's just the change of variable theory. Now you're changing your variables, and these are random variables with the function. If you take the logs, you're going to get a log of PZ1. You get rid of the product. It's going to be a summation of log of P of Z. Here I had the inverse of these gradients. The determinant of the inverse of a matrix is going to be equivalent to 1 over the determinant of that matrix. Okay, a little bit of linear algebra. That's why that summation is going to turn into a negative. Okay, so this is just a change of variable theory. And now we are going to use that. And this is where this residual structure is going to come in. For your F, you can assume a particular form, maybe in a planar form. What is that? Z of t is exactly this h of t here. Z of t plus 1 is h of t plus 1 here. You have a vector u that is getting multiplied by a function h. You have your z vector, which is a vector. You are multiplying it by another vector. This is going to give you a scalar. You add a bias. Whatever that's going to come out of this h is going to end up being a scalar. So it's going to be a scalar times a vector of the same size as z. Why are you doing this? Because you're putting a lot of structure on this function f to make sure it is bijective, to make sure it is invertible. And it is still not enough. This planar structure is not going to give you that. You need to make some assumptions on u, some assumptions on w, some assumptions on b to be able to make this function bijective. And let's assume you manage to do that. And there is actually a paper about that, trying to make planar normalizing flows. If you manage to do that, you can actually write down your probability distribution from one layer to the next one. The probability distribution of the next layer is related to the probability distribution of the previous layer. And then you're going to use this theorem for this particular form of your function. And by the way, u, w, and b are the parameters of your function, of your neural network, which has this structure. Okay? The details don't really matter. In the end, what you're going to get out of all of these operations. Initially, you know the probability distribution of your first layer. That's just a normal distribution or a uniform distribution. This guy you initially know. These values you're going to compute, and therefore you're going to know the distribution of the next layer. Now that you know the distribution of this layer, you can go to the next layer using this formula. And then you keep doing that. And at the last layer, you have a nasty probability distribution, a complex looking. That's going to give you your normalizing flow. That's going to give you Q. And you know your target density. This is your target density, either in the form of 1, or in the form of 2, or in the form of 3. Somebody gives you a target density. So that density, you know, this is the density coming out of normalizing flows. You can write down the KL divergence. It's just a distance between two distributions. And then you minimize that distance. And what are you minimizing with respect to? You are minimizing with respect to these U's, W's, and V's. And then you do your training, and that's going to give you an approximation to your distribution. This is the target distribution. This is the distribution that is coming out of Q and normalizing flows. And it's not that bad. These are complex distributions, and it's not doing that bad, to be honest, given the constraints that you're putting on your function. So it needs to be bijective for you to be able to write down this theorem. So next, I'm going to go ahead and make normalizing flows continuous. So we are going to use ODE solvers. But is everything clear so far? Yes, no? I need to hear a couple of yeses. So the question is, the normalizing flow is the output of the last layer? Exactly. So the output of the last layer is going to give you your normalizing flow. And actually the process, the fact that you are using a change of variable theorem and this particular form for your function f, and then you're stacking multiple layers of that on top of each other, the entire thing is going to give you your normalizing flow. And you can summarize it in your Q exactly. So does that answer your question? Okay. I think the concepts are going to become even more clear and simplified if we go to continuous version. Things are going to be much simpler. Continuous normalizing flow, you look at this operation here that is similar to what you had for residual networks or recurrent neural networks. It means that you can replace it with an ODE. So z dot is equal to f of z and time. For this, I want you to refer to the paper. This is the equivalent of the change of variable theorem in the continuous regime. For the proof, look at the paper, but this is the actual theorem in continuous time. The derivative of the log of your probability, and you can see the log of the probability is showing up there also with respect to time, is equal to, this is now nice. This is beautiful. You still have that matrix that you have up there. The log term and the determinant term, they're gonna collapse into a trace of a matrix. And the trace of the matrix is the summation of the diagonals of that matrix, diagonal entries. So this is beautiful. As a byproduct of making things continuous, you are getting something nicer. And I'm gonna tell you why this is nicer. First of all, previously you need to do a lot of work to make your F bijective. Here you don't need that for the theorem to work, so you can get rid of that, F being bijective. F doesn't need to be bijective, the F that you're using here. Another byproduct is this determinant. The determinant term has a cubic cost to be computed. So this is a matrix. It's gonna have a cubic cost in terms of the size of that matrix. Computing the trace is linear in terms of the number of elements of this matrix. So this is much cheaper compared to that. It means that you're gonna be able to work with neural networks that have bigger size, bigger number of neurons. So you can have more neurons here, okay? You can have wider networks compared to what you have up there. Your loss is still gonna be this loss. And your Q is a bunch of ODE solves. If you want to have multiple layers of ODE solves, that's fine. Or if you want to have a single ODE, that should be fine also, okay? Because you can have a lot of neurons in your neural network. So to increase the capacity of a neural network, you can either add more neurons or you can go deeper. With a regular normalizing flow, you're allowed to go deeper. But if you want to make your neural network wider, the size of this matrix is gonna become bigger and bigger. And because of the cubic cost, there is a limit of what you can do. What is the result? You get similar performance or even slightly better. You're approximating this part of your distribution better, but you're doing it much faster because of the linear cost of computing the trace. Okay, so far so good. Any questions? Because we are not done yet. So we saw an application for continuous depth residual neural networks, we saw an application for normalizing flows and approximating density and density estimation. The next one is about time series. We can do time series analysis. And these sorts of techniques, I guess, are going to be useful even beyond machine learning. We can use them to do scientific computing. Maybe you have an ODE, it is parameterized, and you want to fit it to data. For instance, you have SIR type of models for COVID-19 these days. That one is going to be an ODE. It's going to be in the form of written in the form of susceptibles, infected, and recovered people, or even more complex models with more variables. It's going to have some parameters in them, like the infection rate, etc., or how infective is this disease, or how fast do people recover. These are the parameters. And then you can fit your ODE to your data that you're collecting from perhaps the US or maybe the entire world. Okay, so these types of methods could have applications beyond image classification. And it's nice that you can backpropagate through ODE solvers. Let's see another application for time series. For time series, you have observations. And your observations for this framework do not need to be in particular regularly spaced times, maybe every day. Why? Because on Saturdays and Sundays, maybe there is no data. There is no measurement if you are working with the stock market type of data. Or they don't have to be regularly spaced. Sometimes you have some data, sometimes you didn't collect data, and so on. So these are going to be your data. Your observations are X at some times. You're going to say that my observations are going to perhaps come from a normal distribution, or this is a choice that you're going to make. And the mean is given by a latent variable, and that's the variance. Or maybe a mixture of Gaussians, multiple Gaussians, if you have multimodal distribution. So you make some assumptions here for your data, and then your latent variable, your hidden variables, are going to solve an ODE. It is similar to what you do with recurrent neural networks. And then initially, you're going to sample P of Z from some distribution. Now, what is the cool thing now? You know P of Z. That's an assumption that you made, perhaps normal assumption. You push that through an ODE solver with a complex function, which is a neural network. And that ODE solver is going to give you some outputs in between. Okay? You take those outputs, you push them through this other distribution, and that's going to give you the distribution of your data. Why is it nice? Whenever you have the distribution of your data, what can you do? Can somebody answer? Whenever you know how probable your data is, what can you do? So backpropagation is close, sample more data is an idea. GAN is not that much close. Simulate more of it, yes, but confidence bounds, it's even more fundamental. How can you get these parameters? Initially, they're going to be wrong, randomly initialized. Your neural network is confused. Exactly. So you can maximize your probability, or you can maximize your likelihood. You can write down your likelihood. And as soon as you write down your likelihood, you're done, because then you can minimize your negative of the log of the likelihood, which is your loss function. Okay. And that's going to give you a loss function. And then you're going to optimize it with respect to the parameters of your F. But to be able to optimize and do a stochastic gradient descent, you need to have access to the gradients. And how do you get the gradients? You're going to backpropagate through your ODE solver. Okay, this is why you need this. And then this is a simple toy example. You have some observations in time. The green circles are your observations. The blue one is the prediction. And then the red one you're extrapolating. And those data are getting generated by your ground truth. So you're doing time series analysis. You're predicting into the future. Okay? Any questions about this now that you have the entire picture in front of you? So was everything clear? I need to hear a couple of yeses. So yeah, in terms of the big picture, we started with the motivation that residual neural network, recurrent neural network, normalizing flows, and many other type of architectures that we saw, they were using this formula. This is similar. It's as if you're discretizing an ODE, which is this ODE, which you can solve it using any black box ODE solver. The question is, yes, to do a forward pass, I'm going to solve my ODE, but I need to have my gradients to optimize these parameters. How am I going to get them? And this is the framework to do it. You're going to do it through adjoint sensitivity method. And that's going to give you the gradients of your loss with respect to not only your inputs, but also your parameters. Okay, this is the math behind it. Where can you apply it? You can replace residual connections with continuous depth residual connections with ODEs. You can replace normalizing flows. And as a consequence of that exercise, something nice happened. Rather than paying a cubic cost to approximate your distribution, you are paying linear cost. And then you don't need to worry about making your F bijective. You can also replace recurrent neural networks with continuous time ODE solvers. With recurrent neural networks, you're going to need to have your measurements in perfect timing, perfectly spaced time steps. But here you can get rid of that. You can just do your measurements whenever you want. And as you can see, these measurements are all over the place in terms of the time steps. And then you can do time series analysis. One thing that you do with time series is you want to predict the future. These sorts of framework is going to have applications beyond classification, beyond time series analysis, beyond normalizing flows and density estimation. You can use it to fit an ODE to your data. For instance, for our days, you can apply it for COVID and the equations that you have for the propagation of COVID within your population, or even for drug delivery and etc. So it's really useful to be able to backpropagate through black box ODE solvers. I think it's a good time to stop. For those of you who have questions and want to stay, I'll be around. And for those of you who have classes, other appointments, you can leave. Okay, any questions?
Like right when you're from the very start, when you're talking about reverse mode automatic differentiation, I mean, I get how this thing looks like an ODE, and then you can use ODE solvers, but then you get to like the adjoint stuff and then the gradient of the adjoint. And I'm just like, I have no idea where these things are coming from or why they even make sense. It was really confusing starting from there. And then it makes me have no idea what's going on with these normalizing flows.
Yeah, that's fine. So it's a lot of things to process, which is fine. First of all, if I give you this residual neural network, forget about ODEs. What do you need to do? You need to input an image, which is going to be your H0, and then use this formula. That's going to give you H1. Then you take H1, put it here. That's going to give you H2, H3, H4, and at H capital time or HL, you're going to stop and say, I'm going to write down a loss. And then now that I have a loss, I need to take gradients of my loss with respect to the parameters of these layers. Am I right?
Mm-hmm. Yep.
And this is what we have been doing so far.
Yeah, and then that's how you know how to adjust the parameters of the layers.
And then you do gradient descent. Okay, that was for one image. You can put multiple images through these operations, and that's going to give you a mini batch.
Yep.
And then you just average the loss for every single example. So there is always a loss behind the scene. Okay.
Yep.
The same thing is here. There is going to be a loss behind the scene.
Okay.
Which you are going to optimize with respect to the parameters of this ODE. Am I correct?
Yes.
The same way that you had a loss behind the scenes when you were optimizing these parameters of your residual network. The same way here. So far, so good. Now the question is, how do you actually compute them? How do you do backpropagation? What is going to be your chain rule here? You know the derivative of your loss with respect to the last layer.
Yep.
Okay, so you know this term. This is known.
Yes.
This is equivalent to the chain rule, but this is in continuous time.
Oh, okay. Oh, so A. Oh, because A is the previous one.
Yeah, then you're going backward.
Okay.
A, you know.
Oh, what I am.
H at the last time step, you know. So these two guys, you know. One of them is coming from your forward pass. This A at the final time is coming out of you knowing the derivative of your loss with respect to the output. This is easy to compute because you know the formula for your loss. It is just cross entropy. You can do it analytically.
Okay. Yeah.
So this guy you know, this guy you know, and then you are just solving two ODEs backwards. One is this guy, the other one is this guy. In the end, what you are interested in is A0, okay? But to compute A0, you need to know what is your H.
Well, you're interested in A of all the T's, right? So that you can adjust the parameters at all levels.
Exactly. But throughout the process, throughout the ODE solver,
Uh-huh.
you're going to get all of these. You're going to get
Yeah.
A at every single time, from the capital time up until the first time, like
Uh-huh.
like the formula I have here, from the final time up until now. And we are going,
Oh, okay. So that's just like, so when you're doing that integral, it's more like I should think of it more as like is it kind of like not a sum, but like a product of all the chains in a sense, or like
so no,
uh,
just think of it as an ODE solve.
okay,
So you have an ODE solver, which is going to solve it for you backward in time. And then
interesting.
the simplest one, the simplest ODE solver is going to take this form. This is just Euler discretization, okay?
Uh-huh.
And then this could be backward, yes? H of t minus 1 is h of t plus f of h of t. And then you're going backward.
Okay, I see. And so interesting. So when you get to that like table over there, that's like using more complex variants. So that's using Mangakata, and then some other even more complex ODE solver in the ODE net.
Yes. So ODE net is using a fancy ODE solver, which you don't really need to care about. You don't really need to worry about. If you take an ODE course, then you're going to care about it. But for now, you can just download a package or import a package in Python and then just use it. Just import the best ODE solver that you can find in Python.
And
Okay?
the main takeaway is that you're sacrificing memory or time complexity for some memory complexity.
And not
This
really.
method?
Not really. What you're computing, what you're worrying about here is the order of the computations, the time complexity in terms of the layers.
Okay.
And your layers are the time steps. Okay, you don't worry about how big these matrices are going to end up being or how big these systems are going to end up being. You don't worry how many entries these vectors have.
Usually.
Yeah, because those you can actually solve them in parallel. You can do fancy stuff with them. What you cannot parallelize is from one iteration to the next one, from one layer to the next one, because you have to wait for the results of the previous layer. That's why you're only reporting the order of the complexity in time, in terms of your layers.
Okay.
And it's really hard to define what is a layer here when you have continuous depth. Maybe it's the number of time steps that your ODE solver is taking. Okay, that could be your L tilde.
Gotcha. Wait, so then the main takeaway is, so okay, it's not necessarily pushing the state of the art in these things. It kind of is, but it's that it could generalize to different tasks.
Exactly.
Is the important takeaway?
Yeah. Not only you can do, maybe it is the cheapest way of using ODEs for classification. Maybe it's the cheapest way, but maybe there are some more interesting tasks, like normalizing flows, approximating densities, doing time series analysis, doing scientific computing, doing drug delivery, a lot of interesting things.
Okay.
If you're interested in time series and your data is not in regular grid in time, then that's a good idea to use this.
Okay.
You want to do normalizing flows because it is much cheaper. Computing the trace is much cheaper than computing the determinant.
All
right.
Okay. Yeah.
I'm not sure about the continuous depth because I'm not sure how good it is going to be when you apply this to ImageNet and beyond. Okay.
That makes sense.
But the main takeaway that I want you to take home is this part of the slide. Okay. How this is really important, how to backpropagate through ODE solvers. This is beautiful. This is the contribution of the paper. And this paper won the best paper award in 2018 from NeurIPS. Okay, so it's a very important contribution.
Wow. All right. I guess that's wow. Okay. Cool. Yeah, that's all I had. So thank you.
Okay, perfect.